Okay, so I'm going to go over this one problem with the positron. So the problem is that we have a positron, which is a antimatter electron. So it's the same mass as an electron, but it has a positive charge. And it's going at some very fast speed, called V1 equals 0.8 c, 0.8 times the speed of light. And then we have some region over which it's accelerated that's a 1 meter long accelerator. And I'm just completely making this stuff up, okay? Just making it up. And then we want it to come out of there, same positron, going 0.9 c. So we want to increase from 80% the speed of light to 90% the speed of light over that 1 meter distance. How do you do that? Well, you make an electric field in here. And let's say it's a constant electric field, E. And we know that if you have an electric field and a charge Q, then the force on that charge is going to be Q times E. So that force is going to push it forward and make it speed up. Okay, now how do we find this electric field needed to get it to that? If you did this, F net, there's only one force, so F net equals dp dt. That's the momentum principle. And you can say, oh, look, the momentum's increasing. We can use real momentum too. But what about the time? You don't know the time that this thing takes. And it's not trivial to find that out. And here we're dealing with distances, so when you're dealing with distances and you don't care about time, a little signal should go off in your head that says, wait, I should use work energy. So if I have work equals the integral of F dot dr equals a change in energy, that should be fine. And I can even find this work since I have a constant electric field that doesn't change. This integral just becomes, and the electric field is in the same direction as the displacement. This is just Q, E, D. That's the work done. Now I just need to set that equal to the change in energy. Now here's the mistake that you should not do. If you said this is, oh, well, it's K delta, it's K2 minus K1 plus M2C squared minus M1C squared, to take care of the mass energy, that's fine. But when it's moving that fast, you don't have a good expression for the kinetic energy. Instead, we should just deal with it as the total energy. So we'll just say E2 minus E1, where E in general is mc squared over the square root of 1 minus v squared over c squared. So that's my energy. So now I can just do the change in energy that way. So let's just put in I know my values for the velocities, and I know that, so let's just put it all together. Q, E, D equals E2, where I'm going to have this mc squared for both terms. 1 over the square root of 1 minus, now I have 0.9 c squared over c squared, so it's just going to be 0.9 squared. Minus 1 over the square root of 1 minus 0.8 squared. And now the mass of an electron is equal to, I wrote it down, I always forget this, 1.109 times 10 to the negative 31 kilograms. The charge of an electron is 1.6 times 10 to the negative 19th coulombs. D is 1. So I can solve this for E. Divide both sides. QD. C is 2.99 times 10 to the 8th meters per second. So now let's plug and chug, baby. Just put it in there. And I already did this. Okay, I'm not doing this in my head. I did it on the calculator. I get E is 3.194 times 10 to the 5th newtons per coulomb for the electric field. And that actually, I guessed, okay, I just guessed, but that's actually a good value because now a real accelerator is not going to have air in there because if you have these positrons going really fast, bad things, that interacts with the air. We don't want that. But if it was air, if you have 3 times 10 to the 6 newtons per coulomb, that's the electric breakdown value for air. So that electric field are higher, then air becomes the conductor, and that's when we get sparking. So, but that's less than that, so that's good. But that's it.